My name is Brian Kelly. I'm also an MBA student at MIT Sloan, and very excited to introduce the next team of presenters. Joining us from Germany here, we've got Gabriel Anser, Pascal Bauer, and Dennis Fassmeyer, who are going to present on the detection of tactical patterns using semi-supervised graph neural networks. Welcome, guys.
We're happy to present this joint research project that has been conducted by experts from a German soccer Bundesliga club, from a university, and from the German national team. And the objective of the approach we're going to present is basically the automated detection of tactical patterns using positional data. And although our method can be used to detect multiple patterns in soccer and in different sports, we're going to show this today by the reference of overlapping runs, which is a tactical pattern. In soccer, I'm going to introduce by the following video. And actually, you'll see a bunch of overlapping run situations, so after that video, it should be clear what we're talking about. You see here, number 20, Riedle Baku, a player of the German national team, is being overlapped by his teammate, which distracts kind of the defender and opens him the opportunity to dribble inside and assist a goal. You'll see a different situation where the two players involved in that overlapping run are kind of highlighted. So you see, again, a player on the wing in possession of the ball and a teammate overlapping him. Again, here they choose the option that he dribbles, the player with the ball dribbles inside and takes this beautiful shot. You'll see in the next video that once such an overlapping run is conducted, you also have the option to pass the ball to that player who has kind of a speed advantage because he's coming from behind. And this opens up an opportunity as an offensive pattern as well. And the practical relevance now is, as you can imagine, or as you see in the video, this is an important pattern because it can create chances that are valuable. And of course, coaches are interested in playlists, right? So after some match days of a season, they want to see all our overlapping run situations. Maybe they want to see all the overlapping runs of the opponent, or as you see here, they want maybe a playlist of all the overlapping run situations leading to a goal in German Bundesliga. And the traditional way to create such a video playlist is actually that match analysts or video analysts watch hours of video footage, tag those scenes manually, so they watch 90 minutes of a match to find at the end maybe, let's say, 8 to 10 overlapping run situations. They do that manually, put them in a playlist and present it to the coach. And this is kind of a tedious and exhaustive task, which is not maybe where we should spend the time of those experts that should have, or that have their strength in analyzing the nuances of those situations and kind of analyze and provide insights to the coaches on why a situation has been conducted good or bad, right? This is kind of the practical motivation of the approach. We bring on the next slide kind of a scientific motivation for this. So in past year Sloan papers across different sports, we've seen a bunch of approaches that aim to detect tactical patterns on a group level. We've seen one in basketball this morning as well, which we could add here. And all those approaches used a feature extraction, as we've seen this morning, and an exhaustive labeling setup to feed those labels into a supervised machine learning approach. Then another methodology applied is to avoid this feature extraction, to put the positional data, those spatiotemporal data, into an image representation, which allows us then, or the authors here, to detect patterns on a team level. Again, all those approaches required exhaustive labeling data. We've seen an approach using image representations and CNNs this morning as well, where maybe the computing intensity is another problem. Then last year, graph neural networks has been introduced as one way to represent the spatial temporal positional data in a permutation invariant space. That has the big advantage that it allows the authors there to detect both group tactical patterns as overlapping runs are, where only two players are involved, but also team tactical patterns as, for example, counterattacks or counterpressing. In football, again, the biggest problem there is that a huge amount of labeled data is required, and that's why we're going to present an approach where we use this graph neural network representation of positional data and combine it with semi-supervised approach so that the amount of labeled data required to train such an algorithm is drastically reduced.
Yeah, and now to get a little bit concrete, our model directly operates on inherently unordered position data of the players and the ball. And to capture the temporal dependencies in the data, we use a recurrent neural network as a methodological tool with shared weights that processes each of the players' trajectories individually. And here, thus, we maintain player-wise hidden states ht-1. Now, these states serve as a node representation of an assumed underlying graph structure, and therefore, to capture interaction patterns among the different players, we update these representation using a graph neural network architecture. And now, since the derived vectors additionally encode neighboring information, the GNN output can be basically used to describe the entire interactive path of the different players. And now these vectors serve as input for our encoding modules that output latent realizations, YT and CT, so variational autoencoder-based methods basically assume a data-generating process with hidden or latent factors, which in our case, or more generally in the semi-supervised case, corresponds to the label values YT and some continuous factors CT. And these latent realizations are now used in conjunction with the interactive vectors to basically reconstruct the data. So that is to predict the next movement of the players and the ball. And all these computed quantities, so these movement prediction and the latent realizations, are then passed on to the next time step, and this whole forward path starts again. And now, to summarize what is important here, essentially the two functionalities the model is able to carry out. On one hand, the model learns here the distribution of the data, so it essentially learns how the different agents behave on the pitch, so it can be used, for instance, for trajectory forecasting or game simulations. And on the other hand, it argues over the label space. So this other part here is essentially a deep classification network, and since it works semi-supervised, only requires little manual labeling effort to achieve good generalization errors, and therefore it's also a really good tool for player-level detection task in that sense. And the key model component for achieving good results in both of these tasks is this part here, so the graph neural network architecture that captures the inter-player dependencies. Yeah, and thus it's worth investigating it further. Now, namely, it is designed in a way such that the model is able to adaptively consider different ranges of player influences at prediction time. So, and since interaction with nearby players are decisive in most cases, we use a k-nearest neighbor approach when aggregating neighborhood information within the single GNN layers. However, this does not mean that we eradicate influences of distant players, since, as can be seen here, our architecture contains multiple of these GNN layers whose functionality yields implicitly increasing neighborhood ranges with increasing network depth. And we then also implement a variant of skip connection where the final feature representation directly aggregates from all the node embeddings of the previous layers, and by doing so, we basically allow the final output to contain both information about immediate player influences and also a more holistic team strategies and formation dependent on what interaction structure is best suited for the task at hand. And since now the model nicely encapsulates both the sequential and the interactive aspect, it can be used for detecting important but complex tactical patterns. And here are two examples from the test game, along with the predicted probabilities at each time step of that game. And so this part here, bottom right, is essentially the output over the variable YT we have seen previously when discussing the model architecture. And we can clearly see that the model learns the underlying pattern that describes overlapping runs, underlined by a sharp increase in probability values when the pattern of interest starts. And exactly, and we also compare our method quantitatively against a fully supervised approach and a rule-based baseline. And this table here essentially tells us two important things. On one hand, it emphasizes the advantage of our semi-supervised strategies in situation with expensive labeling effort by performing significantly better than the fully supervised version across both detection tasks. So human experts only have to provide few annotated situations for the model to perform reasonably well. And we also performed better than the task-specific rule-based approach, which basically shows that our method is not restricted to a single case, but can be applied more generally to whatever pattern a human annotators provide in the end.
The question that now arises is, how do we put this into practice? I mean, Pascal earlier mentioned that one thing is just the time saving of automatically identifying those video sequences, like the video at the beginning that we showed that was automatically identified over the Bundesliga season, but there are further use cases. For example, we can perform long-term trend analysis. So here, for instance, looking at the Bundesliga data of this season, we see that which teams, how frequently use this method, this team tactical pattern of overlapping runs, and also how often is it just a distraction, how often is a player actually being passed to. So for example, here we see in the top right that TSG Hoffenheim, our next opponent in 2 weeks when we're playing against them as Hertha, they use this very frequently and often also pass to these players. So we can use this in the match preparation to know what to expect. Furthermore, we can see which players typically do this behavior. So we see that in the Bundesliga season this year, the German international David Raum was the one who most frequently used this action by overlapping his teammate, in this case Andrej Kramaric, who was bypassed 52 times, and they created a significant number of shots and goal-scoring opportunities. Additionally, it can also be used to see when looking at the next opponent, what pairs really mesh well together, and who you should warn your players to who could do this pattern very often. So in this case, we see that Ginter overlapped Sané in the German national team very often. So when you're playing against them, you can tell your defenders, okay, you need to help out when those two are in a situation where this is possible. Furthermore, as mentioned earlier, this is not just applicable to soccer or football, however you want to call it, but also to other sports. In general, you could apply it to virtually all sports where there's tracking data. And one thing we did do was to use a public data set of tracking data to look at the movement and compare our model, our underlying movement model, to state-of-the-art models. And we see that in every aspect we outperform state-of-the-art movement models on a public data set of basketball tracking data. So in conclusion, we have identified and solved a problem of the automatic detection of tactical patterns, which is applicable to a lot of different sports, and that requires very little manual effort. I mean, we've used only limited number of games compared to other approaches that are more labeling intensive. It achieves a very high accuracy, and we can not only identify those group. Oh, sorry. Oh, good. Yeah, okay. It off so we can identify group tactical patterns or individual patterns, like let's say in basketball screens or in football routes run by wide receivers, but also on a team tactical pattern we can identify expected possession value or these sort of things as well. And what I really want to stress out, and sort of the reason why all three of us are up here, is that this research was only possible because we did the interdisciplinary exchange of both experts from the domain and from the university to arrive at such such insights. Yeah. So thank you very much for your attention. Sorry for the sound quality issues, and I'm happy to take any questions.
Thank you very much for making me do a bunch of homework yesterday, reading your paper. The architecture is advanced, I guess, to put it one way, and I had to come up to speed. I'm still learning some of these things. I don't recall. I think in your paper, did you do a comparison to a rules-based approach? Yeah. Convince me why a rules-based approach wouldn't be sufficient for something like overlapping runs, which seems like a relatively simple thing to detect with rules.
Yeah. So, I mean, we did compare to the rule-based approach, and the rule-based already had a pretty high accuracy, so you can determine a lot of those cases, but one thing is a data quality issue, that you don't always identify the exact passing moment in the tracking data with the ball data not being accurate, so that is one thing. And then it's also not quite defined in a way that only overlapping runs only occur in a certain area of the pitch, but it also depends on the context of the other player. So it's so if the opposing team is more shifted to the front, then it will be different. So a rule-based approach that could detect this would have to be a lot more advanced and not just saying in the last third of the pitch and so on. And I mean, we purposely picked a simple thing like overlapping runs to show, but we can, yeah.
But you can apply it to any maneuver that you want. Okay.
Exactly, yeah.
Thank you.
Yeah, I mean, I thought there was a lot of, state-of-the-art kind of combined in novel fashions that we just don't see in sports analytics a lot that you did in this paper. And a lot of useful applications, too, for, like you said, identifying different, types of plays. However, I think the results, the section 4, I just wanted to see a little bit more on that. Can you maybe go back to that slide and just talk through what else you can maybe visually present in terms of, instead of just that, the next slide over, I think it was?
Which one?
The overlapped runs.
This one.
No, the big table.
Yeah, the big table.
Go ahead.
Keep advancing.
Sorry, what should I?
No.
Oh, yeah. This one here.
Yes,
okay.
yes.
Okay. Yeah. I mean, we want to also highlight the application of on the German national team, and that's a bit difficult because you don't have always the same 11 throughout the season. So that's why the matrix here is a bit more sparse than you would have for a Bundesliga team, for example. But yeah, so you can see which combinations happen more frequently than others. That's basically the entire message of this table here.
So maybe if you just looked at one Bundesliga team, that would have been a bit a different, obviously, view than looking at the full German national team.
Exactly, yeah. I mean, we use it on our club level regularly for match preparation for the opponents, and then it's not as far. So actually, to condense the message that is condensed given to the coaches is just the top 3 players in the action that have most frequency. So we don't want to bother them with such a complex representation.
And maybe I could add a little bit on how we can actually apply that to practice. I mean, we select the players as the national team from different clubs, right? So they don't play that much with each other. And so, for example, if we played an opponent last year who defended very deep, it was Liechtenstein, right? They really parked the bus. And the deeper an opponent is, the more effective overlapping runs is. So it was one focus of our coaches to say, hey, we want a lot of overlapping runs. And then we had all this data and could see which player interacts quite good with who, right? And if you look at, that's the darkest green point at Leroy Sané being the offensive winger and Matthias Ginter being the right back behind him, they are doing that pattern quite frequently, although they don't play at the same club, right? And this is an information that helps us to prepare for such matches, for example.
Okay, great.
So thanks. I like my colleagues, I was getting up to speed on this stuff. It's very, very high tech and nice. And I'm just trying to understand what the, relative to. Well, I think. Tell me if I'm wrong, but what's nice about this approach is that when the rules get complicated, right? this is able to pick up some of those things. So I think that in terms of the applications, this is a very simple, clean application that you could argue, all right, maybe a rules-based approach isn't that difficult. But if you start thinking about Brian's world in American football, there's very complicated combinations of plays, right? And fakes and decoys and other things that are really important. It seems like this approach could be really valuable there, right? And go a lot further than, say, what typically is done. So I think that's kind of interesting. And I also think of hockey as being another application where you have a number of things going on. But it'd be really nice to kind of tease out what that extra benefit you get is from that complicated, right? So like how difficult it would be to write down some of those rules and what the extra predictive power you get from that, or sorry, not predictive power, but descriptive power in this case, where you're trying to identify certain situations.
Yeah, I mean, the beauty is that we don't need for new things that we want to identify. We don't need to specify new rules, but just present some labeled data, and much less than with other approaches. So, for example, when we had a coaching change at our club, and he had a different definition of something, we didn't need to collect 40,000 new labels of a more complex tactical pattern, or let's say, I don't know, in hockey, some face-off solution, or in the NFL, some type of, I don't know, rub route or whatever. That's more complicated, and then you can just provide just a few labeled data of a couple games, and it's already enough to have it then be able to identify those for all future games that you want automatically.
I was going to say, presumably you can even learn about new strategies we don't have a label for, right? There's potential, I think, to extract something that you see. You'd have to label it in the context of, the moving parts you have in the model. But you could say teams that do this, and let's assign a name to it. It seems to increase the probability of winning. I think that's very interesting. So, thanks.
You guys were quick, so I get one more question. I'm curious, just for my own selfish education. I know you had a small set of training tags to train the model with. What makes us semi-supervised beyond that?
Well, there was one paper in the machine learning community from Kingma et al. At 2015, which basically proposed to deal with the semi-supervised situations by learning a generative model. So by basically maximizing the likelihood of, or more specifically, the variation lower bound on the likelihood of a semi-supervised data set. And intuitively, like often it is not clear why certain things work, but intuitively, can I go back to the, so in the situations where, we pass this forward, and then this data reconstruction basically operates by giving this YT and the CT to the decoder. And intuitively, the model assigns high probability values in an unlabeled case to the label values that accurately reconstruct the data. And having this data generating assumption that consists of label values and some other continuous factor, CT, it kind of operates in this way in unlabeled situations.
Like a GAN would? Like it's creating fake, trying to trick the model by giving it?
Yeah, like if you think, for instance, like an overlapping run has a different pattern than a classical pass. We guide this model by a few annotated situations. We guide them into the right direction, and then it basically detects in the unlabeled case, okay, which label value has a higher chance of reconstructing this multi-agent trajectory in the end. And that's why, by incorporating the surplus of information, we incorporate more also discriminative information into the model and into the weights.
Thanks. It probably takes a lot more time to explain,
Yeah.
but I appreciate it. Thank you very much, guys.